Fantastic. Thank you, everybody, so much for giving up your time to come and see my talk. And obviously, thank you so much to the InsomniHack team for giving me the opportunity and privilege to be here and talk to you today. My name's Rick. I'm a senior security researcher at Orange Cyber Defense. And my main focus of research is operational technology. So that's what I'm going to be telling you about today. I'm not going to do this many times, but could I have a very quick show of hands? Is anyone unfamiliar with operational technology? A few, that's okay. Okay, so I'm not going to be... this isn't too much of an obvious slide. So, a few devices, I'm going to be speaking about them throughout the talk. So I just wanted to provide a little bit of a definition. So starting at the left, we have a programmable logic controller, or PLC. And this is kind of the main focus of operational technology. It's kind of the last bastion between the digital and the physical realm. This is the thing that will, according to its configuration, sense the physical environment and actuate pumps, sensors, robots, servos, and those kind of things. This will have local monitoring as well, which is usually done with a human-machine interface, which is the middle thing, or HMI. These can be found all over sites in operational technology, typically closer to the environment, the more they will have an impact. So the one that you can see has a touch screen. And that can basically affect the physical environment. You can kind of tell a PLC what to do. They typically will have what's known as a mimic that you can see on the screen in the picture, which will be something like a diagram of the physical environment to tell engineers what's actually going on, so how full is a tank or something like that. And then finally, I won't be talking about these too much or maybe at all, but remote terminal unit or remote telemetry unit is something that does a little bit of control, but it's mainly focused on telemetry and that kind of thing, which will be sending critical alarms back to an alarm management center or something. We'll be focusing on PLCs and HMIs for the most of this talk, though, so don't worry about that. Has anyone been to a conference like this or been somewhere and seen an operational technology attack demo? Another quick show of hands. Has anyone seen anything like that? Okay, that's quite common then. They're pretty much always science fiction. They're not possible in real life. You'll typically see the adversary in that kind of situation turning the entire operational or physical process into a Rube Goldberg machine of catastrophe, and there'll be things going wrong, and there'll be things flying over everywhere and exploding or whatever. And the problem with that is the expected precision of that manipulation of that process is way, way too high to actually be realistic. Those kind of attacks really do require this massive time and financial investment on the adversary's part to be able to do something like that. Either that, or obviously they've got some sort of incredible technical capability coupled with this supernatural understanding of how the physical environment is actually put together. And those pictures on the bottom are proof that I'm also responsible for doing these science fiction talks as well. But hopefully, seeing the technique that I'm going to talk about today, you'll see that we try and bring these a little bit more towards reality. But Rick, you're saying there have been demonstrable attacks in operational technology that genuinely do have these sophisticated sort of effects on the physical environment. And obviously, we're talking about operational technology. I have to get Stuxnet in there somewhere. But it's well understood that it took multiple state adversaries a lot of time and effort and money to actually be able to pull an attack off like that. And as well as that, these adversaries typically have human intelligence agencies to physically infiltrate the environment and get out all sorts of information and a lot of investment in that kind of thing. We actually kind of did an investigation of this quite recently, and we did find that these, at least on publicly reported attacks, sophisticated OT cyber attacks are particularly rare. So we looked at it as far back as we could of evidence of these cyber attacks going back to 1988, so before I was born. And we found that not only obviously are we seeing a lot more recently, they're pretty much always IT attacks. But as you can see kind of across that the actual sophisticated ones that right on the bottom row are really small in terms of the proportion of how many we actually saw. Now, the reason that this is difficult is because if an adversary does get into an operational environment, they can't really just use typical IT reconnaissance and enumeration techniques. They can be dangerous. They can knock over PLCs. And if you're trying to do a sophisticated attack, starting to collapse things in the physical environment is a really good way to tip off the victim that you're there and you're doing weird things. Also, you can't really identify what these assets are doing within the physical process. If you think of it like a web server, you can use Nmap to scan a web server, and if port 80 or port 3 is open, you know that there's some sort of web service. But you need a browser to actually do anything sophisticated with that web server. That's much like a PLC, where you could see, for example, port 102 open for S7, or port 502 open for Modbus. But you don't know what it's doing, you don't know what code is on the PLC, you don't know what it's doing in the physical environment. So what I'm trying to say here is that the adversary literally cannot do anything precisely in that physical environment because they have no way of understanding it. The diagram on screen is the Purdue Enterprise Reference Architecture, or more commonly known as the Purdue model. Now, don't worry, this isn't the whole way that we design operational technology environments. This is kind of more or less a talking piece nowadays of just describing where we might see devices. But the things I want to point out are the levels 4 and 5, which are the typical IT of the environment, and levels 3 through to 0, which are the OT, and they're sandwiched, they're sandwiching levels 3.5, which is the demilitarized zone. And that's important because I want to get across the concept that in operational technology, we're still very much focused on network segregation as pretty much the main focus of security. So far, what I'm trying to say is, in the IT, we have these talkative, resilient assets that will easily facilitate reconnaissance and enumeration and conducting these complex attacks. And then in the operational technology, we have fragile assets that will fall over under the slightest kind of touch. And they will prevent the propagation of these complex attacks because they are difficult to understand. Going further, even if you can start to understand things in the operational environment, perhaps we've found a mimic from an HMI, and we found the kind of the diagram of the physical environment, or perhaps we found piping and instrumentation diagrams. Even if we have those, we still don't know how the PLCs are actually using those things. So getting from that to actually writing some sort of exploit code for it or whatever is still really challenging. So what do these demos that I was ranting about before not consider? Why are they essentially science fiction? And they don't consider a tactic in operational technology attacks that we call process comprehension. And what process comprehension is essentially a way that the adversary builds an understanding of how the operational technology is facilitating interactions with the physical environment. Now, it's a complete requirement to actually conduct process comprehension to facilitate any sort of sophisticated attack. Anything less is essentially what we would call a nuisance attack, or just triggering basic HMI functionality. Anyone can send these PLC stop requests from Metasploit, or anyone can brute force an HMI login page, which is essentially a basic web server. For this talk, we're not interested in these low precision, low hanging fruit attacks. The only problem with process comprehension is that typically it's done by these state adversaries, and they have human intelligence agencies that will exfiltrate certain things, or they will infiltrate the environment. But if we're a cyber attacker and we don't have access to these large intelligence agencies and a lot of funding, how do we perform process comprehension if we've just compromised an operational environment over the internet? And that leads us to process comprehension at a distance, and I didn't name the technique, so I'm apologizing already for that. To conduct process comprehension at a distance, we've got a few criteria that we want to hit. We want to be able to understand what the OT assets are doing to the physical process, and how the code within the PLCs is facilitating those interactions with the physical assets. Obviously, we want to be able to do that over the network, because we're attacking over the network. We're not there physically. And preferably, if we want to do a sophisticated attack, we don't want to be seen, so we want to do this in a stealthy manner. Now, the pictures that I've been showing you so far are all Siemens devices, and that is for a reason. It's because the main devices that we perform research on are Siemens, and we don't hate Siemens. In fact, it's because they're pretty cool and they've got a big market share. However, this actually does affect multiple vendors. This is a systemic problem with how operational technology works that I'm going to be talking about. And yes, we have done responsible disclosure, and no, there are no CVEs, and no, there have been no advisories, because we'll get to that later. So I want to start talking about how PLCs are actually coded. So there's functions, which aren't very interesting. They do very simple functionality like arithmetic. They don't have their own dedicated memory. They rely on what is known as the global variable block, or what we'll call the global variable block. And I'll explain variable blocks in a second. What we actually are interested in are function blocks, which do provide more complex functionality. They may be controlling communications, they may be counting things, they may be actuating things. They have their own memory, their own dedicated memory, and that's what we're going to be calling local variable blocks. Now, these variable blocks, they store variables, input, output, internal variables for the code. They can be global and local, as I've alluded to. And it's an unofficial term. It's what we use for the research because we weren't focusing specifically on one ecosystem. You may see in the Siemens ecosystem, they'll be called data blocks. In Alan Bradley's ecosystem, they'll be called data files. I'll try and stick to variable block. If I say data block, I'm very sorry. I'm kind of used to using one specific terminology. So these function blocks as well, then they're not typically coded ad hoc per operational environment. They're usually dragged in from library. So as you can see on screen, this is TIA portal for Siemens, for coding Siemens PLCs. And on the right-hand side of the screen, what you can see are the library functions which we would drag in. And these are problematic for a few reasons. The first is that they're very standardized, because we're using the same thing over and over, and they're very structured in a certain way. But the other problem is that they are proprietary. So we can't view the code, and we definitely can't edit the code. So if there are any problems with them, there's nothing we can do about it. So if we actually want to start performing process comprehension at a distance, we need to understand the function blocks on the PLC. Sorry, the telly went funny. So knowing the function blocks will help us know what the PLC is doing in the physical process. We can't do something really obvious like use the vendor software to pull the PLC code. That would tell us what function blocks are on the PLC, but that would also tell the victim that we're in their environment, because any rudimentary monitoring software will find that immediately. But I've just said that every function block has its own local variable block. So when a user actually deploys this function block, a library function block, a local variable block, a standardized set of memory is also generated. So the small screenshot is the function block, and the large screenshot is a portion of its accompanying local variable block. So HMIs, for example, and other devices on the OT network will want to access this local variable block to be able to present a diagram of what's actually happening in the physical process. And we can just abuse that legitimate access and do it ourselves. And by doing that, we can enumerate the local variable blocks that are on the PLC, and therefore enumerate the function blocks that are on the PLC. There are a couple of kind of obvious methods to start with. For example, the top one, getBlockInfo, basically pulls metadata for each local variable block. And you can see in the example output on the right-hand side, it looks quite nice, and we'd probably want to do something like that. Alternatively, if we wanted to use the block upload function, it just pulls the entire thing. And again, it's not very pretty, but it does tell us what we want to know. However, the only problem there is that while we can identify the function blocks, it's extremely noisy over the network. These commands are basically never used. So again, if we do something like this, alarm's going to be going crazy. To do this stealthily, we just look at how the HMI does it, which it performs bytecode read requests, and these are frequently seen on the OT network. So our malicious traffic of doing the same thing just blends in seamlessly with the legitimate traffic. And we can actually already narrow this down to what function blocks are running, because if we actually look at the length of in bytes of these local variable blocks, some of those are actually unique already. So we actually know already a few of the function blocks that are on the PLC. However, that's not completely reliable. It's only a few of them, and we want to have a reliable signature-based system. So we have to go a little bit further. If we actually look at how the variables are arranged in memory, we can basically use that to work out a signature. Every local variable block for each library function block has a predefined amount of memory, and it's always laid out in a standardized way. However, it's not been used very well. The example from the first variable in this local variable block that I'm showing on screen is a Boolean, and it needs 1 bit. However, it's allocated 2 bytes, which means that it always has an extra byte that is never used. It is always zeroed out. And that's quite interesting, because if we combine those two, what we find out is that we have a signature. So if we combine the variable block's length and also where there are zeroed bytes guaranteed, we can actually work out a signature for pretty much every library function that we come across. In fact, the Modbus comload there in the first 30 bytes has 3, and this has about 300 bytes. So there are quite a serious number of inefficiently used bytes in the memory. So this is what the tool output looks like when we're doing this kind of thing. We are literally just looking for zeros, so we are just finding zeros. So that's where we're actually identifying something. So the process goes as follows. The first one is we perform these read requests at a local variable block, and we calculate the local variable block's length. And if we found a unique match already, that's great. We can put that one aside and go to the next one. If we don't find a unique match, we can then check where the 0 bytes are, and then by that point, we've found, pretty much definitely found a match. We'll then just repeat that for all of the local variable blocks. There are a few occasions where if someone actually does have a custom function block, or we've not seen it and not signatured one, we won't be able to identify those, but those are rare occasions for the 2 of them. Going a little bit further than that is we can identify these function blocks, but we're actually pulling out all of the variables. And if we know what we're looking at, we know where the variables are because they're highly structured, which means we actually know the content of all of the variables as well. So at this point, we're not just building up what the PLCs are doing, we're building up exactly what they're doing at that point in time. So again, on the left-hand screenshot, you can see the function block, local variable block for our library function. And at the offset of 4 bytes, we can see that it's expecting 9600 as a value. And in our output, I hope you can just trust me for this because I'm not going to do the maths on screen, that works out to 9600. There are a few other different types of variables that are also interesting to look at. So, for example, in a local variable block, if you have a large variable, it will just do a pointer to the global variable block, which I mentioned before. But fortunately, we can literally just decode where the pointer is pointing to, go to the global variable block, pull that out, and then we can start extracting credentials, which is also quite fun. Now, as well as having a read function, S7com, the protocol, also has a write function. And we precisely know where the variables are that we're looking at. So we can actually write to the process as well, and then we can start manipulating the process at a bit level. So there are 4 types of variables. I'm not going to go through them all for the sake of time, but default variables, which are quite common, we can literally overwrite once and it will permanently overwrite. So we own that variable. Direct, indirect, and pointer variables also have certain conditions that mean that if we do want to persistently overwrite, we will have to continuously send a write to that particular point of memory. But that's also not that difficult, and as I was saying, these kind of things are expected over the network, so they're quite stealthy anyway. So what we've talked about so far is just comprehension and manipulation of the process. So we can perform process comprehension at a distance, and there was only one method that was interesting. We saw 3. The first 2 were really noisy, so we decided not to do that. But we went with this bytecode read request. And by sending these read requests, we can ascertain the length and the 0-byte offsets within the local variable blocks, which then gives us signatures for library function blocks. Because we know where the variables are, we can then start extracting some fun stuff, so communications, creds, algorithms, and things like that. And it's also possible to manipulate variables by sending these write requests. But we've got a load of unused memory in PLCs that is never monitored, it's never checked, and it's basically ours. So depending on the architecture of some sort of OT network, it might be the case that we've managed to deliver malware to some sort of water treatment facility or some sort of electrical substation that doesn't allow contact back over the internet. So if we deliver this malware, we can't exfiltrate data, and we can't actuate the malware in any way. So if we assume like a distributed architecture, maybe water treatment, for example, simplified in the diagram, the compromised HMI, which you can see in the blue box, can't connect outside of the field site. It doesn't have internet access. And the compromised SCADA server in the cloud can't connect to the HMI, so they cannot talk to one another. However, both the compromised HMI and this compromised SCADA server both have legitimate reasons to be talking to the PLC. The HMI will be presenting the mimic on screen, and it will allow engineers locally to actuate things, and the SCADA server will be pulling data out for telemetry, monitoring, and all those kind of reasons. So the PLC that is highlighted in red can essentially be used as a proxy to set up a command and control. So the way that we do that is essentially both the server and the client enumerate their function blocks, and they identify common memory regions that are just zeroed out. And they can use these for control and data transmission. We just need 2 bytes to do this. The first byte is for synchronization and control, and then any additional bytes is just extra bandwidth for the command and control. And the C2 allows us to essentially execute commands at a console or terminal level or whatever that we've compromised, and the only restriction is the privileges that we've ascertained when we compromise that machine. So I've got a quick demo. Well, not demo, it's a video, because there's no chance I'm doing a demo. I don't do things like that, because I'll definitely mess it up. So the Windows thing that we're going to see here is we're going to say that's the HMI, and then there's also obviously a Kali box, which is going to be the attacker. So just to prove it, oh no, it's doing that. Basically, it's 172.21.1.5 is the IP address of the client. And our adversary tries to ping that, and we can't get access. So they can't talk to one another. However, the adversary does have access to a PLC at 172.21.1.1. So both the client and the server will enumerate the common memory regions in the local variable blocks on the PLC. And we'll go through, and this is what it looks like when our tool's running. It's obviously not very pretty, but I mean, it works, so that's good enough. And we'll basically find what's going, and the tool is going to say, oh, it's a certain length, so it's probably going to be this specific library function block, at which point we get to now. Down. So it'll say it's Modbus comload, or Modbus serial, and then it will check the 0 bytes. We'll do that anyway for posterity and verify that. And then we'll say we want to set up the server on this, this data block, or local variable block. The client will do the same, and they're both ascertained the same memory regions, and they're both talking to one another. And then, yeah, we've started communication. We can send our command. The client receives it eventually. It's only got 1 byte as bandwidth. And then we get to popcalc. Cool. So one of the criteria was that we wanted to be stealthy. So we wanted to test whether we could get through best practice prevention and detection controls. For prevention, we used typical firewalls on remote and local network segments. And for detection, we used monitoring to detect any malicious or anomalous behavior that was going on in the network. We had 9 use cases because we were working in academia at the time and we had to be as thorough as possible for our sins. And I'm not going to go through them all again for time. And we conducted this in sterile conditions. This was conducted at Lancaster University in their industrial control systems lab environment. And yeah. For prevention, we found that for any untrusted devices that are on the network, it did correctly prevent most of them, some of them not. That was quite embarrassing for them. However, prevention did actually fail quite a lot for trusted devices, which is understandable because trusted devices sending what is expected to be legitimate traffic on the network, such as read and write requests, is extremely difficult to isolate and extremely difficult to block. And that's made worse by the fact that industrial firewalls, despite being industrial firewalls, don't really offer granular traffic filtering more than just the specific industrial protocol, so S7 or Modbus. Some modern firewalls do allow us to go a bit more granular with certain rare commands, like the ones that I mentioned before that we opted not to follow, like get, block info, and upload. But nothing as granular as read and write requests, and especially nothing as granular as those to very specific addresses. For detection, we used Clarity CTD, just because that was the detection engine that we had at the time. Other detection engines exist, so we didn't have any preference there. And what Clarity CTD does is it baselines any legitimate traffic on the network under normal working conditions, and any deviations from that baseline are obviously detected, or any known malicious traffic or previously unseen devices also raise alerts as well. So standard attack tools like our T5S, which is just an Nmap top 20 from the client, was detected, the C2 client, which is fine. So we obviously wouldn't want to do things that were going to be really obvious and detected easily. But when we were just doing the read and write requests for process comprehension and manipulation and the generic C2, nothing was detected. Not really. It was detected as an event, but everything is detected in as an event. So what it said was baseline deviation, but not a risky change. So what does this actually mean for defense? Prevention, yeah. The techniques described here are intended to be used when you've already breached the perimeter. So it's quite difficult to vouch for network segmentation when you're already in the network. And it's not really feasible to put a firewall with and granular enough inspection to stop specific read and write requests to certain memory regions in front of every PLC. Not only is that going to cost a load of time, cost a load of money and take a load of time, it's really quite risky to try and block those addresses, block read and write to specific addresses. Detection as well, it was a little bit better. Like we did see certain things were detected as and alerted on, but not really anything that we were doing for this specific tooling. If we did actually try and start alerting on read and write requests, it would start causing alert fatigue. It's not something that is really particularly feasible. So again, it's not something that is really something we can do. So we're kind of wrapping up. I think that was quite quick. That's good. A quick one-slide recap, and then we'll talk about responsible disclosure. So most demos that you've seen, as I mentioned before, are works of science fiction because they say that, oh, you can do all sorts of attacks and everything's going crazy and the attacker just magically knows how the process is set up, which is something that takes a lot of knowledge. This research actually did bring those attacks closer to becoming a reality. I am not saying that this solves the attacker's problem and this makes it trivial. There are a number of limitations to this, but it does bring it closer to reality. By utilizing these read and write requests, it's possible to execute these really high precision process comprehension and manipulation. With creative use of those same techniques, we can circumvent best practice network segmentation with the PLC-facilitated command and control. And detection and prevention is very difficult, and it's not there yet. And if these techniques are used in the way that they're intended, it's pretty much going to mimic ordinary traffic, and it's extremely difficult to detect. Now, finally, for the vendor responses, we had 3 main responses from them. The first is that the asset owner should implement certain security options. All of those suggested security options were off by default, which is already a problem. But if we did actually implement those specific options, it can either limit or completely stop functionality. So, for example, in the Siemens ecosystem, we can use what's known as block optimization, and it squishes everything together. But then the HMI that was previously talking to it wants to find the very standardized memory addresses, and it can't anymore. And this starts a cascade where basically nothing will talk to each other and nothing works. So if you want to turn on those security options, be prepared to spend millions on replacing every piece of operational technology in your environment, because otherwise it's pretty much pointless. The other one was separate the affected devices with network segregation. The command and control broke that, so that doesn't really count either. And finally, the affected devices aren't our recent models, and they weren't actually the recent models. But what they were was the most prolific, best-selling models, and some of the models with the highest market share worldwide for every vendor. And finally, these PLCs just do tend to stay in service for decades. So if they do go out of production, we're not going to see them disappear anytime soon. So this problem is going to be around for quite some time. And without talks like this, the customers of these vendors still don't know about this attack. And that's me. Thank you very much. 3 things on screen. Top one is the preprint of the work I've just spoken about. The middle one is a preprint of our most recent work, which me and Charles are presenting at RSA 2 weeks' time. It was literally just accepted for full publication in Digital Threats Research and Practice Journal 3.5 hours ago. So that's pretty cool. And finally, the Security Navigator is our flagship research output, pretty much. So check that out. My work for OT content, it's not this kind of research, it's kind of higher level. That's on page 107, so check that out as well. And thank you very much. I'll accept nice questions.
Hello, thank you for a great talk, especially that it's uncommon to have talks on attacks on the ICS side, not on the SCADA side. So this is actually a very interesting research. I was wondering, because you showed the technique to figure out the functional blocks, but I was wondering if you actually looked into somehow reverse engineering slightly farther, because you can figure out the blocks, and based on the variables, but you don't. Can you actually figure out also how they are connected to each other to actually reverse engineer, let's say let's call it control flow of the actual software that's actually running there? Because otherwise, you know a specific block that's doing something, but it doesn't actually tell you exactly where in the whole process this is, right?
Correct. I perhaps wasn't clear enough. I might have actually not even said it. So basically, this would go hand in hand with other elements of process comprehension. So, for example, quite early on, I showed, for example, the mimic of an HMI and piping and instrumentation diagrams. And we'd use other elements of working around and finding bits and bobs are all around to basically put them together. But like I did say, this is limited, and this only brings us closer to these sophisticated attacks becoming a reality. It doesn't completely solve the problem. There are some other issues as well, such as certain function blocks will be controlling multiple pumps or valves. So we actually can't definitively say that something is doing just one thing. I was flippantly going to suggest that we could do something with AI, or machine learning, but that's as far as we wanted to go with this research. This was kind of put to bed, so it was kind of out of scope for the research at that point.
Thank you.
We got two up there.
Hello.
Hi.
Thank you for your presentation first. So I have a question about the attack path here, because this is directed to the PLC. Mm-hmm. Okay. Is it easier to go directly there or the HMI where you are supposed to find all the instructions for the PLC? Well, so on the attack path level, would it make more sense to go to protect the HMI?
To protect the HMI?
I mean, no,
to attack it?
Over, yeah, to target. Sorry.
I mean, it depends what you're trying to achieve. But if you want to go to the source of the functionality where you can actually find out what's going on the PLC and manipulate that, going directly for the PLC is easier. But at the same time, there's nothing stopping you from also going for the HMI as well. Typically, HMIs do have a bit more kind of traditional looking functionality, like web pages that you can get into. So you could go for both. Like this is just one part of an attack. It's not supposed to be the entirety of an attack. Yeah. So yeah, is essentially.
It was more about from your experience and from your research, what would be the top priority to look at for the defensor side, let's say?
PLCs, absolutely. Yeah, because they are the last bastion. They're the things that are actually listening to or sensing the physical environment and actuating things. So that is where you really want to be protecting. That is kind of the crown jewels, so to speak.
Okay, thank you.
Over there.
Sorry. Hello, thank you for your presentation. Have you ever used all of this outside of a lab, or at least to actually guess an industrial process that you had no knowledge on in the first place?
You wouldn't catch me using this in a production environment, no. Unless it had been shut down. But no. Which is a fair comment. Like, this hasn't been used in a real environment, but the principles do work. Like, this isn't something that is different in a real environment. This, for all intents and purposes, our lab is a functioning water treatment facility that we did this on, and it was put together by engineers that work in water treatment in the UK and critical national infrastructure. So it was specifically built for that. So there is no difference between that and an active water treatment facility.
Demo would be cool. Thanks.
Thank you for the talk. Siemens is one of the most widely researched industrial PLC manufacturer. So they had the privilege of being tested by Orange or others. What do you think about the rest of the ecosystem?
Of the Siemens ecosystem?
No, the PLCs, actuators, and so
on. They're all really good. And they do the operational functionality extremely well. It would be extremely challenging for them to implement security really well. And it's very unfair for me to stand on stage and just bash them and say they are bad. They aren't. They do what they are intended to do very well. It's the nature of how operational technology runs. That means it's extremely challenging for the vendors to implement security, and more so to retroactively implement security controls in an OT environment. So to an extent, this is essentially bullying. But yeah, they do what they do well. For security, they're trying, they're getting better. I'm personally not happy with a lot of the responses to responsible disclosure. But yeah, I can't really say anything more.
Yeah, thanks for the really interesting talk. Just a quick question. Like, I know that you're focusing specifically on more advanced, sophisticated attacks, but if you go on a random Shodan Safari, you can find HMI interfaces on the internet quite easily. Any comments on that, or like what issues can be achieved through those sort of hunts and findings?
Every so often you'll see a big study that will come out and it'll be like, oh, there are 8 billion ICS devices or OT devices connected to the internet. And what those studies fail to take into consideration is that the serious majority of them, like high percentage of those, are just academic researchers setting up honeypots. And you'll see that these studies will consider things as OT devices connected to the internet, and they're not even like high interactive honeypots. These are things like conpots that are really, really basic, and they are quite obviously a honeypot. They're signaturable as a honeypot. So while there are definitely devices connected to the internet, the recent Unitronics PLC HMI thing, for example, where the Aliquipper water treatment was attacked, and there was one in Ireland as well, I don't think it's quite as prolific a problem as is made out. I'd actually be really interested in doing a study on that and kind of doing a counter and saying, actually, no, they are mostly honeypots, but I actually don't know how to do that at scale. But yeah.
Thank you for the talk. If I understood correctly, you had to compromise the HMI and the SCADA to conclude your attack?
That was just an example of how the command and control would work.
Yeah.
It's not necessarily the only way, and it's not necessarily the way to do it, but it's just a demonstration. Okay.
Because as I was wondering, as we know that most of them run on Windows, shouldn't we focus to secure those hosts before securing the PLC?
The study that we recently did last year, we looked at as many publicly reported OT attacks as we could find. And the main criteria were it had to have actually impacted the OT, so the process had to have been impacted. And also it had to have been a cyber attack. So, for example, certain boats hitting certain bridges, even though people may have called that an OT cyber attack, it wasn't verified, so we wouldn't have included that. And what we found was that 61% of all of those attacks were conducted by cyber criminals, and they used IT-focused tactics, techniques, and procedures. And essentially what came out was, since 2020, most of the OT attacks have happened, and they're pretty much just ransomware on the IT, and the OT is taken offline as a precaution, or a dependency in the IT is taken down, and then the OT has to shut down because they can't keep processing. So what our advice there was actually nothing to do with protecting your OT. That is a future problem. And it's more reduced to those dependencies and focus on the resilience of your OT and segregate it as much as possible. So yeah, you're absolutely correct. It's pretty much still an IT problem. So yeah, this kind of thing is probably not making it much easier. But at the same time, yeah, you are correct. I agree. Any more for any more?
I have one, actually. What are your views on the IEC work and the standardization of PLCs and taking into account cybersecurity in that?
So the specific standard on like secure by design, where they will verify specific individual assets.
The electric community. So you have a
so 62443, right?
Yeah.
I think it's good. I think it's one of the only standard sets that is actually OT focused, and it does actually provide the guidance that is specific for that. It's very much focused on management from what I've seen. I've done one of the qualifications, one of the entry level ones, just to do it, and yeah, it was good, but yeah. I mean, it doesn't really have much competition either, so it kind of is. It doesn't matter if it's good; it's the only one.
Yes. Great.
Okay.
Thank you.
Thank you very much.